Hey there, calc folks. Back here with another video where we're just going to continue our study of the limit, where we are going to start looking at some technique for evaluating limits. All right. Some technique beyond just relying on graphs and tables. All right. Graphing and tabling functional values to evaluate the limit is really a preliminary technique. And one of the things we should note with respect to that technique, it is a bit more of a support technique in terms of supporting your final answer as opposed to being the technique that you want to rely upon on confirming your final answer. All right. In terms of proving your final answer, we might say. Right? We had mentioned in class that graphing and looking at tables and drawing conclusions about what the value of the limit is in that technique, in that method, is really just inductive reasoning. Right? Graphing is kind of pushes the edge of inductive and deductive. However, by just looking at the graph, we are doing a little inductive reasoning. What we want to be able to do is take that reasoning a little further. And that's what we're going to do in this next couple of sections of notes. And I am going to try to keep these videos short. I got a little bit to say in each, but they're all going to be related to evaluating limits here, folks. So this is going to stretch out over, I think, a couple of videos. This bit of material on evaluating limits. Let me bring it into view here. Right? Like I said, what we're going to start taking a look at is how to evaluate a limit. Right? Where I begin is just by noting here for y equals f of x in this statement, right, that we're all becoming familiar with. Determining the value of L really does involve analyzing the behavior of the function f of x near the value of x equal to a, right? It does involve an analysis of behavior, right? An analysis of behavior for the dependent value of our function near this independent variable where x happens to equal the value of a. And that analysis can happen, right, with a lot of different components to it. Graphing and tabling are just two of the components, two of the preliminary components, or like I had said, more of a check component to the process. We want to go a little beyond that and in our work incorporate some equational analysis, right, into evaluating a limit, right? We want to be able to look at a limit statement and from just the limit statement itself without having to really consider what might the graph look like overall, right? Or have to actually sketch the graph, right? Or have to break out a calculator to sketch that graph. Begin to perform some sort of equational analysis on our function f of x, and particularly on it, looking at that functional output near this value of x equal to a. Right? And where a good portion of this analysis occurs, or what a good portion of this analysis involves, we might say, is to begin with analyzing the continuity of our function f near or at this value of x equal to a. All right. What we're going to find out is that continuity is going to play a big role in the value of our limits. All right. What we're going to find out is that in order to be continuous at a point, the value of the limit, right, is also going at that point is also going to have to equal that dependent value at that point. And that the result of continuity, right, at a point is going to be drawn by actually using the meaning of a limit. So if we see continuity, right, at a point, we're going to be able to use those conclusions for continuity to be able to say that that limit exists at that point, using a technique that relies on that continuity. All right, a technique we're going to actually just call substitution method, right? And that's going to be a technique that we're going to see ending this bit of notes, right? But these techniques are developed in the following set of notes here, right? And where we start this set with is we are going to be looking at limits of real values and commenting on the idea of continuity. All right. We are going to be looking at, to begin with, limits at real values. What I mean by that, right, is in this limit statement, we are looking at the limit as x approaches a, where in these arguments, a is going to be a real value. Right? A is not going to be a value that approaches positive or negative infinity, as we've seen earlier in the notes. A is going to be a real value. It's going to be a location that exists specifically along a number line, and we should be able to point to that location. Something you can't do with infinity or negative infinity. You can point in their direction, but you can't actually point at them because that's not what it means to be infinity in a sense. Infinity always continues on after, right? It goes on forever in a sense. It's more of a direction than it is a location, is how we might argue that, right? So again, consider this limit here, right? This limit as x approaches a for f of x, where what we're going to think about is a as being any real value, a number along a number line. And what we have come to find, and this is all related to continuity, is that our function that location at x equal to a doesn't always have to exist in the domain of the function. Right? This location that we're approaching in the independent value doesn't always have to exist in the domain of the function. The function doesn't always have to be defined at the value of a. In fact, a lot of the more tougher limits that we encounter in a given semester have to do with the fact that at that value of a, there is a discontinuity, and that our function f is not defined at that value of a. All right? But if it is defined at that value of a, right, what we have is continuity in that function, and with continuity, we're able to draw some pretty quick conclusions with regards to the value of that limit. All right? But let's consider this setup. All right? Let's look at the definition in that setup to begin with. All right? Where I begin here with the discussion of continuity is just by going back and reiterating that when we see this notation, right, that notation where we have an x with a right arrow pointing at the value of a indicates that in our limit, x is going to approach a from both sides. It's going to approach a from values less than a, and it's going to approach values from values greater than a. If we think about a location as a along a number line, x is going to approach that value of a from both values greater than a and from values less than a, right, in its approach. Right? This is what's called a two-sided limit. Right? And how we identify a two-sided limit, it's more of what it lacks than what it has. Right? This is all compared to a one-sided limit. If I follow this definition with that of a one-sided limit, right? The notations for one-sided limits involve those superscripts of negative or positive signs, right? Where those negative or positive signs indicating approaching from the left or the right hand side, right? When we say x is approaching the value of a, it implies that our independent variable x in the function is behaving in both of these ways simultaneously, in a sense. That not only are we approaching from what would be the right-hand side, but we would also be approaching from the left. All right? I first start by just reiterating that idea. And I believe that's come out in class and also earlier in the notes. Right? And in other words, right, if we think about what that implies about our limit, right, for any real number a and function y equals f of x, if we have the limit as x approaches a for f of x equal to the value of L, then what must be true, right? What must be true is that both the left and the right-hand side limits for that function, right, at that corresponding location of a, must also themselves be equal to the value of L and equal to each other. Right? If as x approaches a implies x approaches a from the left and x approaches a from the right, then to say that the limit as x approaches a for f of x is equal to L, right, is to say that the limit as we approach from the left must be equal to the limit that we approach from the right, and those two limits for the one-sided cases must also be equal to the value of L. All right? If this is not true about those two one-sided limits, what we end up saying about the limit of the two-sided approach, right, is that it simply does not exist. Right? And we have a result that's given to us by what's called the two-path test for non-existence of a limit. The first thing we discuss here, right, when looking at evaluating limits, right, is that in the case of a two-sided limit, there is the instances that do occur where the limit, right, results in a solution that simply does not exist. And we say that, right, when asked to evaluate the limit. We say, well, that limit does not exist, right? And when approaching a from the both the left and the right-hand side, we can say a limit does not exist when the left-hand approach does not yield the result that a right-hand approach yields. Right? If the left and the right-hand approaches are not equal, right, then what we end up saying is that the approach from the, right, well, from both sides, right, must not exist. Right? I think I'm going to rewrite that at the end of the notes here. I just don't like how it spaces itself out there. All right? So you might see that change just a little bit, but let's not spend our time there. But that is known as the two-path test for non-existence. Right? If a limit as x approaches a from the left for a function doesn't give the same result as the limit for x approaching a from the right for the function, then the limit for the approach that comes from both directions simply does not exist. All right? One thing we can say also from this idea is that the one-sided limits can always be evaluated. Right? The left-hand limit can always be evaluated. And the right-sided limit, the right-hand limit, can always be evaluated. Right? The one limit that can't always be evaluated, and where we say does not exist, is the two-sided limit. Right? I think I also make note on that here. Note, one-sided limits can always be evaluated individually. Right? You can always calculate this limit in the if statement or this limit in the if statement. You'll always be able to evaluate those individually. What won't necessarily always be true is that they equal each other. And if they don't equal each other, the corresponding two-sided limit will not exist. Right? Note, one-sided limits can be evaluated individually. The two-sided limits are the cases where we can say does not exist. And right? we are going to learn that that is sometimes a common result when working with two-sided limits. Right? That is an option, right, as a conclusion that we can draw from a two-sided limit, right, is that it does not exist. Right? Now, I might consider the limit as x approaches 4 for 3x equal to 12. Right? This is a two-sided limit that happens at the value where a is equal to 4. Right? And what it's again asking for, we've mentioned this again and again. This is all back to what does it mean to be a limit. This limit is asking the function 3x, how do you behave as x approaches 4? It's asking, how do you behave as we approach from values less than and greater than 4? How do your one-sided limits behave? Right? And what we can note is that we're pretty familiar with the behavior of 3x, right? That being a linear function, the behavior is that the approach, right, is actually going to be the value, well, the output is going to approach the value of 12. Right? It's going to approach the value of 12, right? Because the function 3x approaches the value of 12 from both the left and the right-hand side. Right? That result of 12 is supported both graphically and by tables, but it is really more of a result due to the fact that the function f of x equal to 3x is actually a linear function that is continuous at the value of x equal to 4. And being continuous at the value of x equal to 4, whether we approach from the left or from the right, being continuous is always going to have us approaching the exact same value. And that value being the output of the function f at that value of 4. Right? We can conclude that this result of 12 must be the result pretty quickly by simply taking and evaluating our function 3x at of x value equal to 4. That would be 3 times 4. And we all know 3 times 4 is equal to 12. Right? We were able to draw this result, right, actually using what's called the continuity of the function. The continuity of this function at the value of 4. In fact, if we think about the continuity of this function at any value along its, well, in its domain, it is, well, that's kind of a redundant question, but if we consider the continuity of the function at any value of x along the number line, the reason that's kind of a silly question is because that function is always going to be continuous at all values within its domain. Oh, I ought to be careful there. Right? Continuity and domain are not necessarily interchangeable. All right? But what's unique about 3x is that yes, it is continuous at all values in its domain. You got to watch what we say here. All right? So if it's continuous at all values in its domain, it is continuous at the value of 4. And because it's continuous at the value of 4, we can say that f of 4 equal to 12 is going to be the value of this limit. Right? Recall from algebra, right? What does it mean to be continuous at x equal to a for a function f? Is that there are no holes or gaps in the graph of the function f at x equal to a. That when you sketch your graph, right, there's going to be no holes or gaps at this particular location where x equals a. Right? We'll be able to draw the graph from the left side of the x-axis to the right side of the x-axis without ever having to pick up our pencil and shift to some other location in space, or to have to stop and draw a hollow dot in our graph. There'll be a location in our graph at every single value of x along, right, the number line for the case of 3x, right? At what is, in this case, every single value within its domain. Right? Now, in calculus, we take that idea of function is continuous at x equal to a if there's no holes or gaps at x equal to a, and we actually give it a calculus understanding. Right? We note here again as the graph of 3x has no holes or gaps at any value of x over the interval from negative to positive infinity. So f is continuous over all real values and thus is continuous at x equal to 4. And how do we know it has no holes or gaps? Well, it's just simply a linear function. Right? So we're able to draw in the end the conclusion that the limit as x approaches 4 for 3x is nothing more than 3 times 4, which is equal to 12 in value. Right? We're relying on the continuity of the function at x equal to 4 to draw those conclusions. And we can note this is all supported graphically. Right? Here's the graph of 3x. And we can see as we approach 4 for values of x from the left or the right, right? Because of the continuity in the graph at the value of 4 here, there being no hole or gap, right? We know that as we approach 4 from the left or the right, the output of this function is just getting closer and closer and closer to the dependent value we see over here on the vertical axis at the value of 12. Right? What we see now in calculus is a calculus understanding for continuity. A calculus understanding for continuity that tells me if I happen to be continuous at this location right here, right, then the value of the limit approaching this location, right, along my x-axis must be equal to the dependent value of the limit, or of the function, right, at that location. The function within the limit at that location. Right? And what we have is a calculus test for continuity, a calculus understanding for continuity. It's a bit of a test because it sets up some conditions that have to be true in order to be continuous, for instance, at this value of x equal to 4 in this graph for 3x. Right? If you read the test, it says in calculus, right? We didn't really know this before calculus. In algebra, we had to rely on that holes or gap idea. Calculus refines this understanding, is that for a function y equals f of x, it's continuous at x equal to a, right? It's continuous at a particular value of x if the following 3 conditions all happen to be true. If any one of these conditions is not true, it's going to fail this test and we're going to have discontinuity. Right? The first test, right, is that the limit as x approaches a for f of x, the two-sided limit for the value of the function at that value of x equal to a, where you're interested in continuity, must exist. And what that means, folks, right? Remember what that means is that this two-sided limit must exist. Well, sorry, backwards. Let's get this right. If the two-sided limit exists, what that means is the left-hand side limit and the right-hand side limit, which are going to be they're always going to be able to be evaluated, is that they must be equal to each other, right? So if the left-hand approach in the limit and the right-hand approach in the limit are true for the function where we're interested in the continuity, right, at that value of x equal to a, are equal to each other, then the limit for the two-sided approach must exist. And that would be the first condition that has to be true, right, in what we call our test for continuity. The second is that the function f must be defined at that value of a. there must actually be a location in the domain of our function f where we have an output, a dependent value. All right? In order to be continuous there, we have to be defined there in our function. All right? At this value of a, right, we have to have an output at f of a. It must be defined. All right? And then lastly, to be continuous, at a value of a in our test for continuity for a given function, is that limit that must exist for function f of x as x approaches a, and this value f of a that must be defined from steps 1 and 2, or from, we might call criteria 1 and 2, right? They must be equal to each other, right? In a test for continuity, the two-sided limit for the function at the value of x equal to a must exist. The function f must be defined at the value of a, and that two-sided limit that exists and that function f that's defined at that value of a, they must be equal to each other in order for a function f of x to be continuous at the value of x equal to a. All right, that's called the test for continuity. So there's some implication from that. Right? When we know that a function is continuous at this value, where x happens to equal a, when we know it's continuous there, we know that the limit for the two-sided approach exists there because it has to from the first result. And we know that it has to be equal to a defined value. That value being f at a. Right? A result of this continuity here in this graph at x equal to 4 is that we know that the two-sided approach must exist. Right? Because that's a condition for it to pass the test for continuity. And we know that the output of the function must be defined. And we know that those two items must be equal to one another. Right? This final result produces a method we can use to help us evaluate a limit, a two-sided limit. Right? And that is a method we refer to as substitution method. Right? If a function is continuous at a value of x equal to a, right? If y equal to f of x is continuous at x equal to a, then what must be true is that I can take the value of a, substitute it into the value of my function, the input of my function, the independent variable of my function, and that dependent value will be equal to the value of the limit. That's referred to as substitution method. And I bring that up in the notes. So by definition, if y equals f of x is continuous at x equal to a, then, right, the limit as x approaches a for f of x must equal the value of f of a, right? This condition must be true. And what we call this is substitution method for evaluating limits, right? And when evaluating limits, it's often the very first thing you try, right? If I gave you some technique for evaluating a limit, the very first thing you should always try when first starting to look at the value of a limit at a real value, right, where a exists along a number line, is just to take a and plug it into your function f and see what happens. See what result you get. Because if f is continuous at a, right, f at a will be the value of your limit. Right? And there's a lot of times where f is going to be continuous at a, because there's a lot of functions out there, and there's a lot of different types of these, right, in our study of mathematics that actually happen to be continuous at all values within their domain, and happen to be continuous at all values in their domain, and happen to have a domain that stretched from negative to positive infinity. So they happen to be continuous everywhere from negative to positive infinity, meaning that this substitution method works over their entire domain. Right? Now this is true, right, for linear, quadratic, polynomial, rational, as long as it's in the domain, exponential, logarithmic, trigonometric, right, are all continuous at all values of x in their domain. And several of those have domains from negative to positive infinity. Logarithmic functions don't, right? There's a logarithmic function that the input always has to be bigger than 0, remember? There are the 4 trigonometric functions, the cotangent, the tangent, the secant, and the cosecant, that have domain limitations on them. Right? But as long as you're within the domain, you can evaluate them using substitution method. Right? And rational functions are the others that I often think of. Right? Rational functions, you are going to run into domains, right, that don't stretch from negative to positive infinity, that don't exist everywhere along the number line. So you're going to encounter locations or whole intervals where functions may or may not be continuous. All right. So, folks, yeah. Sorry, I had to take a break there. I was interrupted, but I'm back. We were talking about against this method of substitution, and there's a lot of functions where you can apply substitution. I did notice one thing I wanted to say down here, and there are functions where a limit can be evaluated using substitution at these locations. At these locations of continuity. I think that's what I wanted to say there, right? Yeah, because when we think about something like a rational function, we can use substitution on a rational function for every value of x that is in its domain. With a rational function, however, we don't have domains from negative to positive infinity. There will be locations of discontinuity, and at those locations of discontinuity, we can't use the results of substitution method to give us the exact answer. They're going to lead us to some useful information, but those results aren't sometimes conclusive just in themselves, right? We'll show you here in a bit. I think that's my next set of videos, or my next video in this series. All right. Let's look at an example though here, right? Where this is all very useful. I consider this example here. Consider the limit as x approaches -2 for x cubed minus 4x squared plus 7x minus 1 for this function here. And if you just take note of that function, you've seen these before in college algebra. That's what's known as a polynomial function. And what do we know polynomial functions? Those are nice, smooth, continuous curves that begin at negative infinity in the domain and stretch all the way up to positive infinity. So this function is continuous at all values in its domain over all real numbers, right? So the value of the limit, right? The value of the limit, right, is just going to be the output of the function at that value of -2, right? At the value of -2 that we are approaching, right, in the notation for our limit here, right, for in our question of the limit, right, in our evaluation statement, right, implying when we think about the value of our limit and this polynomial function, the limit can be found just by plugging in -2 into that polynomial form, right? Substituting into these locations for x cubed, then minus 4x squared, the plus 7x. Substituting into those locations for x, this value of -2. And through simple evaluation, right, through arithmetic here, we can evaluate this to be the value of -39. Right? Thus, the limit as x approaches -2 for this polynomial function, x cubed minus 4x squared plus 7x minus 1, must all equal the value of -39. And we were able to draw that result from just knowledge of the polynomial function being continuous at the value of x equal to -2. We did not have to make a graph of this polynomial function, which, if you keep in mind, is not always the easiest process, especially when you do not have rational zeros, right? Nor did we have to look at a table of values, right, and draw some loosely related inducted result. Right? We were able to use the deductive knowledge that this polynomial function is continuous at all values of x from negative to positive infinity, so it must be continuous at -2. And by being continuous at -2, that means that those three conditions for the test for continuity must be true. That means that this limit must exist, that both the left and the right-hand side limits give the exact same value for the limit. Right? And that the dependent value for the function must be defined at -2, at this value. Right? And it's defined to be -39. And the last criteria in our test for continuity, right, that allows us to draw this conclusion is that this limit, right, the limit in our test for continuity must be equal to that defined value in its existence. All right? That is what allows us to draw this conclusion about this polynomial function in regards to its limit at x equal to -2 using just our understanding of continuity. Right? And there are a lot of functions that are continuous over their entire domain. So there are a lot of limits from we might say even negative to positive infinity, where they can be evaluated just merely with some substitution method. Right? Where you do have to be careful with continuity, there are a few locations, as I pointed out, rational functions. But rational functions have continuity issues where function f is undefined. There are instances, and this goes back to our test for continuity, where we do have to be cautious of those three criteria to be continuous. All right? There are cases where function f is defined, but we're not continuous at that value. And one of the big places we have seen that in some of our example, I think perhaps some examples in class more so, is in our examples dealing with piecewise functions. All right? So I bring up this piecewise function. All right? Bring this out of the picture here for just a minute. Let's focus our attention here. All right? Consider the piecewise function f of x equals, right? And here we have this two-piece function f, where the first piece behaves as this linear function, 2/3 x minus 2, right? And that's for values of x less than -3. And the second piece behaves as 6 minus 2x, a linear function, for values of x greater than or equal to 3. Right? And what we want to determine, right, I asked for a couple values for the limit. The limit as x approaches 7 for f of x, and the limit as x approaches -3 for f of x. And the first question we should be asking ourselves with these limits in mind, right, is what's the continuity at these values where x is approaching a? What's the continuity of this function at x equal to 7? What's the continuity of this function at x equal to -3. Right? And what we know at x equal to 7, well, that's a value of x that's greater than -3. That's going to put us, right, in terms of behavior on the portion described by this linear function, 6 minus 2x. I can't highlight it all. I'm trying to highlight it all. There we go. It's going to put us on this piece. So it's going to put us on this piece of linear behavior. We're at x equal to 7 on that piece of linear behavior. Notice we are continuous. We're a linear function. Linear functions are continuous over their entire domain, from without limitation from negative to positive infinity, but in this case still at every value of x greater than or equal to -3. So the value of this limit is simply going to be the value of 6 minus 2x when x equals 7. Right? 6 minus 2x when x equals 7 is going to yield us what? -8 in value. Sorry, a sneeze caught me there. As you could see coming on. Where were we? We were evaluating this limit. So again, yes, this because that x is greater than negative, where x is greater than or equal to -3, x equal to 7 is continuous on this portion. We can just plug 7 in there. Substitute in 7, use substitution method. Substituting in 7, we can see -14. 6 minus 14 is going to end up yielding -8. I do think I have that as the next result. If we bring that in to view here, right, we end up seeing that as our result. Right. To evaluate this limit, we just take note of the continuity at x equal to 7. Right. At x equal to 7, f is a nice continuous linear function for 6 minus 2x. So that limit is really just the value of f at 7. And substituting 7 into this function, 6 minus 2x, here for the value of x, we get 6 minus 2 times 7, which does simplify to -8. As for -3, we do have a bit more interesting behavior, most certainly. We can first of all note that at -3, that does play the role of a boundary between the two behaviors that this piecewise function illustrates. All right. For values of x less than -3, we behave as this linear function. For x values greater than or equal to -3, we behave as this linear function. All right. So when we think about evaluating that limit, for this particular case at x is approaching -3, what we need to do is we need to test our continuity at -3. We need to start off by, well, take note, first of all, f is defined at -3, right? If we substitute in -3, well, certainly -3 is going to yield what? I believe it's positive 12, right? At -3, right? When we're at -3, we're still in the second piece. X is greater than or equal to -3 in this second piece. So at -3, we'd substitute in -3 here, right? And 6 minus 2 times -3, the -2 times -3 is +6, so 6 plus 6 would be 12 in value. And that 12 in value would also be the result for the right side limit, the approach of x from values greater than 3. Or, sorry, greater than -3. Right? Whereas from the left-hand side, from values less than -3, we would be approaching on the piece 2/3 x minus 2. And for values less than -3, if we thought about using substitution method here and we substituted in -3, which is more than safe to do, this function does exist by itself at -3. So if we considered what would be the behavior if we were approaching -3 alone in this first linear function, 2/3 x minus 2, 2/3 times -3 is -1. Take away another -2, we would be approaching -3 in value. right? As x approaches -3, the output would also be approaching -3. Right? One thing you'll note there is that the approach to -3 from the left is not the same as it was from the right. From the right, it was 12. From the left, it's -3. So here we have a discontinuity, right? And at -3, because the approach from the left and the right aren't equal, we can say that this limit, as x approaches -3 for function f of x, it does not exist. All right? As for x equal to -3 at f of x, note the discontinuity at x equal to -3, right? It's not continuous, right? Since that limit f of x does not exist, it fails our test for continuity, right? If we take note, did I really get that? I did get that math wrong. It's not -3, it's -4, right? If we take note, the approach from the approaching -3 from the left, if we substitute in -3 here, that's actually going to turn into -2. My apologies. -2 would yield -4. Whereas if we approach -3 from the right, we would approach on the P6 minus 2x. There, I had that correct. We would approach the value of 12. Right? And implying these two one-sided limits, the left and the right side limit, aren't equal to each other for that corresponding case of where x is approaching -3. So what must be true about the limit as x approaches -3 for our function is that it does not exist. We can safely say that in this case. All right? And again, it's due to the discontinuous behavior, where in that discontinuous behavior, that discontinuity, we fail the test for continuity for the first criterion, right? If we think about why we have a discontinuity at x equal to -3, right? Oh, my apologies on that sound. I overextended. Here's our continuity test. This is the part of the test that fails. Right? In the continuity test, you always begin with steps 1 and 2. Those are kind of interchangeable, or criterion 1 and 2. Criterion 1 and 2 are kind of interchangeable in their order. Right? And if you notice for that last piecewise function, this was true. F at A was defined, right? F at A was defined to be -4. Right? That -4 also being this left-sided limit. But the right-sided limit, the limit approaching -3 from the right, was equal to 12, and this was not equal. So this limit as x approached A from both sides for f of x does not exist from the two-path test for non-existence. This is not true. So it fails criterion 1 in the test for continuity. Right? 1 and 2 are interchangeable in their criterion. 3 only becomes the into play in the test when criterion 1 and 2 both pass. Once criterion 1 and 2 both pass, you do want to check criterion 3. Right? There are instances where the limit does exist, f at A is defined, but this criterion 3 fails to be true. Right? I don't know if I get into that in this note set. Here's a graph of that situation. Right? But we will likely see some an example of that case. Right? And if I encounter any of those future in the notes, I'll point that out. I do, or even in past notes, maybe I can dig something up and point that out. All right. But if we take a look at our graph here, here's the graph of that piecewise function. We can certainly see at 7 down here at this location, we are continuous. We do approach that value of positive or of -8, right? The limit as x approaches 7 for f of x is equal to the value of -8. But that limit as x approaches -3 from both sides does not exist. And the reason it does not exist is because the approach from the left and the approach from the right, do not exist. Well, are not the same. My apologies. I'm thinking of that other case. Yeah, the approach from the left has us approaching the value in -4, we can see. The approach from the right has us approaching the value +12, as we can see. +12 and -4 are not equal to each other. These two values are not equal. All right? So that limit for the two-sided approach does not exist. All right? Now, all that's supported here graphically. Now, that other case I was thinking of, you would think that could occur, for instance, if we had a hollow dot right here instead of a solid dot. Perhaps we had a three-piece piecewise where right here we also place in a location of unique behavior. And maybe we have a solid dot up here. And if we have a solid dot up here instead of down here, and this was a hollow dot, that function would be defined up here. The limit would exist down here, but the two would not be equal to each other. Right? And then in that case, we would have discontinuity. The limit would still exist, but we would see discontinuity in our graph. All right? So just in conclusion, and I'll present one more example here also. When you think about evaluating a limit, right? Not only does it require the understanding for the meaning of what a limit statement is saying, right? In terms of its describing the behavior of the function's dependent value as its independent value behaves in this way, right? As x approaches a. And it's saying, yeah, the dependent value gets really close to L as my independent value gets really close to A. As x, my independent value approaches A, f of x is going to approach the value of L. All right. To evaluate a limit, it does require that understanding, but it also, what we have to realize is that understanding can be obtained by understanding f's continuity near x equal to a, and requires us to understand then what it means to be continuous. And in calculus, what it means to be continuous is to pass those three criterion. Where once it passes the first criterion, we're able to say that that limit exists, and we're able to evaluate that limit. Right? When criterion, what criterion 2 and 3 have to deal with, or any three of them altogether, is the idea of continuity. When we see continuity, though, we can automatically jump right over to substitution method, and substitution method works just fine. Right? Where we have continuity issues, right? We want to go through and when evaluating a limit, make sure that we pay attention to the two-sided value by looking at the approach from the left and the right-hand side. We want to pay attention to criterion 1 in that test for continuity. All right. Let me give you one more example here. Right. We might consider evaluating this piecewise function, and this is one reason why you always want to run the test, right? Right, especially when looking at the limit here. You always want to be really cautious. You just don't want to jump to the conclusion, well, this is a piecewise function, and there seems to be, the two pieces separate themselves at -6, you might say. You just don't want to jump to the conclusion that, well, it's going to be discontinuous at -6, and thus that limit is not going to exist. All right? Just because you have a piecewise function doesn't necessarily imply that that function has a discontinuity where any two of the pieces happen to make their separation. that separation can occur in a manner where things don't actually separate, right? You might see that where you have two separate regions in the domain, but the ranges don't separate in value. Take a note here. If we look at the approach from the left, we would be on this piece for -6. And notice -6 times 2 would be -12, plus 14 would be +2 using substitution method. The left-hand approach will always yield a value, and you can get there through some substitution method because you're dealing with a linear function. And it's defined at that value of -6, and -6 defines it at the value of 12. Or, sorry, 2. -12 when you plug it in, plus 14 makes 2. Now notice what happens when you approach from the right. As x is greater than -6 and you approach -6 from the right, you're on the second piece. And if you substitute in -6 for x there, you're taking a -3rd of -6. And a -3rd of -6 is +2 again. Both pieces on their edges near the value of x equal to -6, near this boundary, right, both behave in the exact same manner. They both approach the value of 2. The left-hand approach and the right-hand approach approaches the value 2. And this function, right, this limit does exist. It does exist, and it equals the value of 2. All right? Right? To evaluate this limit, we must understand f's continuity, right? Note each individual piece of the function illustrates a continuous function over its entire domain, right? Both pieces illustrate linear behavior. However, being a piecewise, a discontinuity could exist at the domain location separating the two pieces at x equal to -6. So you really want to consider a test for continuity. All right? Don't jump to the conclusion that it just simply does not exist because we see two different separate pieces of behavior. Right? Note in the test, f of -6 is defined, right? If you were to substitute in -6 to this function, it would go into this first piece, and it would again be defined to be 2 in value. Right? As for the limit, though, it also exists. Because when we think about the left-hand approach, which would equal that +2 through substitution, and we think about the right-hand approach, which also equals +2 through substitution, right? Both yield the same corresponding value, right? That corresponding value of 2, right? So in the end here, since both those left and right-hand side limits pass criterion 1 in our test for continuity, and then what we can also notice here with respect to continuity is because f of -6 is defined at 2, right? And 2 is the value of our limit, right? Because the left and right-hand sides are equal to each other. This function is actually also continuous at the value of x equal to -6, right? The limit here is also noted down here at -6. And we can see all of this in the graph. Right? And I take note, it must also be continuous at -6. My apologies on that sound. It's the word program here. Oh, we're at the end. So note, right, all this is supported in the following illustration here, right? That limit as x approaches -6 equal to 2 is certainly true as we approach from the left and the right, this value of -6 here, we are approaching this dependent value of 2. Right? And it's continuous there. As I draw this graph from left to right, I don't have to pick up my pencil here at -6. Right? There's no hollow dot there. There's no gap or hole. Right? That's because not only does the limit equal 2, but the defined value of f at -6 equals 2. Right? Passing that test for continuity. that's continuity, folks. All right. And the value of limits and how we use it in the process of evaluating limits. Where it plays a big role is in this technique we call substitution method. One of the early techniques for evaluating a limit you're going to learn is just to take the value that the independent variable is approaching in the limit. In this case, it would be the value -6, and substitute it into the function. All right. There are a lot of functions, right, where through substitution you can evaluate the limit just to be the output of the function at that value. Right? It's just going to be the dependent value of the function at that approached value in the independent values. All right? And that's when you have continuity, or at least when you have the first criterion from continuity. But if you have continuity, that first criterion has to be true. And that's what allows substitution method to occur. Now, when substitution method does not point at a real number value, when you attempt substitution method and it does not point at a real number value, right? And you know you have continuity issues, right? You're going to have to take your analysis a little further. The result of substitution, though, in that case, is still going to give you a little bit of information as to how you're going to have to proceed. Substitution method is never a terrible method. The one place you really want to be cautious with it, though, is in the case for these piecewise functions. All right? You really do, in the case for a piecewise behavior, have to be cautious of when looking at continuity and the value of a limit being a result of substitution method is the test for criterion, for continuity, those three criterion. All right. So this has turned out to be a long video, but it does cover the beginnings of evaluating limits, giving us the substitution method, along with, what would we say? Along with also getting into our discussion of continuity, which is a portion of what's in the book that is discussed kind of a little later in the chapter. I brought that up a little bit here. So yeah, we're covering a little bit of ground, most certainly. We have covered a little bit of ground in this video. So I'll stop there. I hope you're doing well. I'll be back pretty quickly here with another video where what we're going to look at in the next one is we're going to go on and consider, well, what happens if we're asked to evaluate a limit where there happens to be a discontinuity? We saw the case for does not exist, right? When we discuss things like piecewise defined functions. However, what also could arise, right, if we're asked to approach a limit where we have a discontinuity, right, the focus here was a bit more on continuous, is going to be that we have the case for what we call an infinite limit. So we're going to get into some discussion about infinite limits next time. Right? And that's going to be the next direction we head with this discussion on techniques we're going to use to evaluate limits. And where that technique, where we look at infinite limits and encounter that case, as we encounter that case, it all begins still with the case for substitution method. We're going to see that. All right. And we're going to find that limits are not going to be as tough as we think. There is, in a sense, a process we can kind of follow. Right? And we have we're going to have a lot of methods to support our solutions. All right. So I hope you're doing well. I'll end the video there and I'll post this up and I'll get into that next video. as soon as I can. See you next time, folks.